As the world is trying to reduce carbon dioxide emissions, the transition to electric power for motors, for various industrial heating applications, is really what the future requires.
The demand for lithium-ion batteries is only going to continue to grow as the adoption rate of electric vehicles increases. Many people don't know that electric vehicles have been around for a very long time.
The electric car is here.
The original electric vehicles lost out to gasoline because we didn't have a power grid that enabled farmers to charge their vehicles on the farm. Now that we have an established grid, we're seeing broad adoption of this technology in the form of an electric vehicle.
More than 97% of grid energy storage is dominated by lithium-ion batteries. In the United States, every year about 4,000 terawatt-hour electricity is used. Lithium-ion batteries will play a major role.
Europe and North America have traditionally cared a little bit more about sustainability and environmental protection and these sorts of concepts when looking at manufacturing. And so they're really interested in seeing the elimination of forever chemicals from these battery cells.
Both push and pull incentives are driving customers to both electric vehicles and consumer electronics being driven by lithium-ion batteries. The example of push are things like government incentives as well as disincentives for buying internal combustion engines. The second thing is the pull, like the ability to charge at home, being able to power your home if there's a power outage, as well as just the cool factor of electric vehicles. They really have been able to rethink the user experience of driving from the ground up. And this has resulted in widespread adoption based on consumer desire. And this can really be disruptive to the entire market and is a big driver of the adoption of electric cars.
One of the things that makes lithium-ion batteries so desirable is they're lightweight, and they also have both a high gravimetric and volumetric energy density. This means they have a lot of energy for a small weight and small volume, which makes them applicable to a lot of different areas. This could include medical devices, tablets, phones, e-bikes, portable energy storage. The average lithium-ion battery can cycle 2,000 cycles with normal use, or 3,000 cycles if you really take care of them. And so this is a desirable function for a lot of different applications.
There's a lot of research going on, both in how do we make a better battery, how do we make the battery faster, how do we make the battery safer, how do we do it with more abundant, more environmentally friendly, more socially responsible materials that have less of an environmental impact, less geopolitical implication, and still deliver the performance that we crave in our vehicles.
A typical electric vehicle requires over 200 kilograms of metal, compared to 30 to 40 kilograms for a conventional car. That's when we exclude the aluminum and steel for the frame. This increased demand for metals is going to drive the mining industry to have to innovate and find new materials. It also means that we have to be very explicit about our ability to test those incoming materials to make sure that they have the right purity and quality.
Mining for lithium is interesting because we're seeing a lot of investment being made in it in areas that it otherwise wasn't happening, I would say even 2 years ago. If you look at the US today, we're enabling mines like Lithium Americas and Ioneer to start exploration, construction, and eventually production of lithium in sources that we feel are secure and our industrial entities will always have access to. There is a geopolitical element to it, I think. We're trying to onshore more manufacturing in Europe and in North America. But as part of that to remain competitive long term, we're seeing a lot of innovation in how we actually get that lithium out of the ground and process it so it's ready to be put into batteries.
There are a lot of raw materials that go into a lithium-ion battery, and I want to segregate down into sort of two categories. One is the inorganic materials, and that really consists of the minerals that are dug out of the ground in order to make the things like the metal casing, the electrodes, and also to make the salt which is used for the electrolyte. And then on the other side, there are the organic materials. The organic materials start from essentially oil, and they're refined and processed to get to the materials that go into the battery. There are four main parts of the battery that get chemical analysis performed on it: the anode, the cathode, the electrolyte, and the separator. So there are analytical test instruments that actually test for each of the precursor chemicals that are used to make up those four different components.
Testing material purity is a crucial part, requiring sensitive detection of trace elemental impurities as well as contaminants that can affect the performance and the lifespan of the battery. For example, lithium brines or lithium salts tend to have high concentrations of total dissolved solids, exhibit high background signals, and also contain high concentrations of easily ionized elements, which can introduce inaccurate results. This is the part where the instruments that are right behind me play a crucial role in the life cycle of the lithium-ion batteries. So from the upstream to the downstream of the lithium-ion battery industry chain, the analysis of macro and trace elements use instruments like ICP-MS and ICP-OES. These instruments are ideal for this application as they combine exceptional analytical performance and robustness.
When you look at batteries research and the materials research associated with it, essentially every instrument in Bruker's portfolio could be used to support that sort of research. When you think about everything from raw materials to mining to electrode and active material production, cell production, and then ultimately module production, there's a lot of quality control workflows, there's a lot of new material development, new system development associated with it.
This starts, for example, with NMR, with our high-resolution ARVON series, with different fields, floor-standing instruments, high-resolution instruments. But that's not the full story. We also have to offer derivatives of this technology on benchtop systems. And here to mention, of course, the Fourier series for NMR, which brings really NMR to the bench, cryogen-free, or also time domain NMR systems, which are very robust with especially inhomogeneous samples.
FTIR, Raman, XRD, XRF to NMR, and electron microscopy and EDS and these sorts of things can help you do everything from making sure the quality of your product is consistent and high, but also helping you innovate and be competitive long term.
The goals of research and development of batteries is to make them economically viable. And there are three components to this: the cost of the battery, the energy density, and then third, the life cycle. Like, how many times can you recharge this battery without it losing capacity? If we think about this in terms of internal combustion engine, if you bought a car and in 1 year it only could hold 1 gallon of gas, it would not be a practical purchase. However, if it only went down in a predictable manner, the capacity of the gas tank, and after 20 years you still had 85%, I think that would be an acceptable exchange for most consumers. So the goal is to kind of balance these three things: cost, energy density, and life cycle.
To reduce the cost of the batteries, first we need to take a look at how battery cost is being calculated. Right? It's calculated as how many dollars per kilowatt hour, which probably already provides some ideas of potential solutions. For example, we can reduce the number of the numerator, right? The dollars, using cheaper materials, cost-efficient processing technologies, or we can increase the cell level energy of the individual batteries that are building blocks of any EV battery pack. For batteries, cathode materials is about 50% of the materials cost in the battery. So to reduce the battery cost, the first materials we need to think about is cathode.
Originally, we had a lot of cathodes materials that were LCO, lithium cobalt oxide. Then over time, we introduced new elements. So then we have lithium NMC. So now we've added nickel and manganese to the mix. And at one point, those were in a 1-to-1-to-1 ratio. Now we've evolved further. We are fabricating cathodes that are NMC 811. So we've reduced the amount of cobalt down to 10%, where previously that number was 100%. So innovations like this are going to help reduce our need for these rare earth metals.
Hopefully, eventually we can develop earth-abundant, for example, manganese-rich cathode materials to completely remove cobalt from the EV batteries.
Researchers are hyper-focused on cost-down engineering to make the batteries cheaper, as well as increasing the range, which means increasing the amount of energy per kilogram. If we think back to my childhood, when you had those battery not included lead-acid batteries that powered toys and other electronic consumer devices, they contained about 50 watt-hours per kilogram. Today's modern lithium-ion batteries contain over 300 watt-hours per kilogram, and research and development is going to push that above 450 soon.
A lithium-ion battery works by shuttling lithium ions between your two electrodes. Current state-of-the-art lithium-ion batteries use an anode that is typically graphite-based. A graphite anode has a theoretical capacity of 360 milliamperes per gram, compared to a lithium metal anode, which is 3,860. So we're talking 10 times the theoretical capacity in this lithium metal anode. One thing we can do is remove that graphite anode and swap in a pure lithium metal anode. Because we're just using a piece of pure lithium metal as that electrode, it's a lot more dense. So that is going to enable a higher volumetric energy density, as well as that high gravimetric energy density.
There's one other element that we really have to pay attention to, which is safety. I always remind people that gasoline can burn as well, but if there is a runaway event in a battery, it is harder to put it out. And so the key is not only durability, but safety. And lots of initiatives going on while we're improving cost, while we're improving longevity, while we're improving cyclability, to also address the safety question.
It's very important that the cathode have 100% quality control inspection. Advanced imaging, spectroscopy, and microanalysis methods ensure that the structure and chemistry of the cathode is appropriate and consistent. The anode faces similar challenges in material consistency. The electrode composition must be precisely controlled in order to maintain ionic conductivity and prevent degradation over time. It's also important to have positive material identification and consistency in the separator. Inconsistencies in the separator can also result in thermal runaway, particularly under extreme conditions, such as the heat in Texas or the cold in Minnesota. Because of these components' size, particularly when combined together into a cell, module, or pack, there needs to be specific form factors and customization available to be able to incorporate analytical technology into the material's production line or near that production line for spot testing.
One of the main challenges to testing the stability and structure of a battery is looking at the evolved gases that are produced during cycling of the battery itself. So if we can characterize what gases are being produced and at what quantities and what rates, it gives us a lot of information about what's happening inside the battery from a chemical reaction perspective. So GCMS, gas chromatography mass spectrometry, is the best technique for this analysis because you can characterize not just the quantity of the gases being produced, but the identity if they're unknown. The sustainability question always comes up in this conversation about batteries. And one of the main criticisms, of course, is that lithium is not an endless supply raw material on the planet, and getting to it is often very difficult. But I think the long-term solution is to perfect the recycling effort.
Everyone recognizes that we're taking precious minerals and throwing them in the landfill. And there's no use in doing that when we could recycle them.
Today's internal combustion engine vehicle is one of the most recycled products on the planet. Almost 90% of the vehicle is economically recycled at end of life, whether it's the steel, the platinum, and the catalytic converters. We are still at the beginning of mastering the technology to recycle lithium-ion batteries. At end of life, that battery still has about 75 to 80% of its initial performance. That leaves lots of opportunity to perhaps refurbish the battery or repurpose it for other applications, for example, for electric grid storage.
Recycling of spent lithium-ion batteries starts out with pulverizing the battery itself. There are blades used to pulverize the battery down into smaller and smaller particles where, when you look at the pulverized battery, it just looks like a black mass. In fact, that's the colloquial expression for the pulverized lithium-ion battery. Important components you can get from this black mass mostly are metals. That's the value to a recycler, is to reclaim the metals and potentially reuse those metals in new lithium-ion batteries or in other purposes. As the battery is recycled, any sort of waste which is made needs to be tested as well, so that we can ensure there are no contaminated waste effluents going into the environment.
This is where X-ray fluorescence, or XRF, comes in. It can provide a very quick analysis of the chemical composition of any element in the ppm range. XRF is a vital technology to be able to identify when black mass has contaminants or other material that may foul the hydrometallurgy or pyrometallurgy process. Particle analysis, particularly with scanning electron microscopy, can also be mission critical. The size and shape of particles is important, as well as the presence of binder or other materials that may have an impact on the process and may determine what process steps are required to dissolve that active material and retrieve those minerals.
We've gone from making a few thousand cells to millions of cells a day. That's a challenge, scaling up production of a physical object so quickly. The workforce isn't there, so we need to teach people how to build batteries safely and effectively. The Battery Lab is a place that was designed from the ground up not only to allow university students, but also industry users to come in and learn how to make batteries in a way that's representative of mass production. This does a couple of things to address these challenges. One, it trains workforce. It gives people a familiarity with equipment that they wouldn't normally see during a standard university education or even at their current job working in an internal combustion engine factory. The other thing that it does is it allows us to build prototype batteries or cells that are more representative of what will go into an electric vehicle. The closer we can get to a full-size cell with our prototypes, the more likely we are to catch early problems or find really great solutions that maybe we didn't know were right in front of our faces previously.
PNNL is training that next generation of scientists. So this includes those who are interested in getting into the field of battery research. So maybe you are a high school student or a college student looking to come here at PNNL and intern. And while here, you really get hands-on experience working in our laboratories, understanding the mechanisms of how a battery works and how we conduct research. So establishing a level of new scientists who have baseline knowledge and can contribute to the field is really critical. A lot of universities don't have courses on battery chemistry or electrochemistry. So if we can get students to come here to PNNL and learn that information, we're creating future leaders in the energy storage space.
As a lab scientist or scientists in universities, professors in universities, we are not really manufacturing batteries. Instead, we are using our scientific tools, our knowledge, our facilities, right, to support industry to accelerate this manufacturing process. For example, we have a facility called the Advanced Battery Facility, which our scientists use every day to make prototype pouch cells, such as lithium-ion batteries, lithium metal batteries, sodium-ion batteries, zinc batteries. So we use those prototype pouch cells as a testing vehicle or testing platform to cross-validate the new materials, the new ideas developed by our scientists and test them at industry-relevant conditions to make sure that the results, the findings are valuable to industry so they can conveniently adopt our technology. The efficient use of our advanced battery facility not only just successfully bridged the knowledge gap between academic research and industry need, but also it helped accelerating the technology translation from lab to market.
So I think a lot about the technology innovation cycle. This is where we have innovation, then growth, then maturity, then decline. All technology goes through this. It's important to note that batteries are still in that innovation cycle. They're not even in the major growth cycle yet. And I'm very excited about some of the innovations that we see coming down the pipeline.
There's the mutual benefit in bringing our teams of well-trained scientists together, and both companies are bringing a well-defined range of expertise to the table, right? On the Bruker side is how to operate and how to develop new analytical methods, how to develop new software, to also, from an R&D perspective, to use these new workflows we are developing together to encapsulate them into software-based workflows and roll them out together with you into production-affiliated environments.
At the Battery Lab, we have the opportunity to see a lot of really early stage cutting edge research. And some of the things that I've been most excited about are efforts that are proactively reducing the most dangerous parts of the battery. And not dangerous to the end user, but dangerous to the people who are making the battery, the areas around the factories. So some of the chemicals that currently go into making batteries can be pretty nasty. And while we have good engineering controls in place that protect our users and protect the environment, it's always better to eliminate those entirely. And that's what we're working on, and a lot of people are working on. So that's quite exciting.
Yeah, I really like the endeavours in making batteries safer, lithium-ion batteries safer. And recently there's been some investigations done around solid-state batteries.
Traditionally, the lithium-ion batteries use a liquid electrolyte that can be replaced with a solid material. This swap unlocks the possibility to store more energy in a smaller space that potentially will improve the range of the electric vehicles and shortening the charging times.
So when I think about batteries trying to meet the needs of society in the coming years, I really think about climate change. Ultimately, we want to decarbonize a variety of different industries, whether it be manufacturing, transport, stationary energy, these sorts of applications. And so if we're going to meet those societal needs with battery technology, we need to continue to innovate from a materials perspective, but also a manufacturing technology perspective, because both of those have the ability to reduce the cost of that energy technology and also improve the performance of it over time.
In 5 years, I can envisage lithium-ion batteries going into electric vehicles only will increase demand by roughly 2 or 3-fold. There is that much demand for electric vehicles, and further out to 10 years, I think with adoption of electric vehicles, there will be an acceleration of the use of electric vehicles, whereby you could expect 6 to 7-fold increase in electric vehicle purchases by 2032, 2034.
No matter which chemistry or which battery technology we are working on, cross-validating everything in the realistic batteries and test everything in the practical conditions are very, very important. If we never step into testing the innovations in practical batteries, right, we will never know if it's really valuable for industry to use in the future. So not only just producing a lot of good papers, but also make sure the knowledge is really applicable and implementable for the real world.
No one would have thought that we would have seen the pace of improvements in energy density, power density, longevity of these batteries at the pace we've seen it in. And it's coming through the combined research across the world. There's no question in my mind that the transition to battery electric vehicles is going to happen. It is the right technology at the right time. Today, the world is approaching 90 million vehicles produced per year. That's about 1 vehicle for every 7 people on the planet. We're just beginning the transition and penetration of battery electric vehicles into that marketplace. And so the demand for the raw material production, for the battery plants, is going to continue to increase, because that transition is the right thing to do for the environment, and it also delivers a better vehicle for the consumer.